Good day, everybody. Today we will be learning about the synchronous generators, and this is the lab manual. And I downloaded the data templates to record the data. So by using these two documents, we'll be doing the experiment, and I'll show you uh, how the experiment is done, kind of thing. So the first thing is the objectives. To first one is to study the no load operation of the three-phase synchronous generator, and then the second section is to study the regulation characteristics of a generator with different loads like resistive, inductive and capacitive loads, and we'll see how the voltage profile changes with different load. And then we'll try to draw a model of a synchronous generator. So in order to do that, we'll be conducting open circuit test, short circuit test and DC resistance test. Remember in the transformers you conducted the open circuit test and short circuit test, same like here we will be doing these two tests, but this is an extra test we need for the armature resistance. So basically from this one you'll get armature resistance, and from these two tests you can find the synchronous reactance. So if you know the synchronous reactance, and then if from these two tests you'll conduct the you will get the synchronous impedance. So from the, if you know the synchronous impedance and resistance, then you can find the synchronous reactance. Basically we need to find the RA and XS. The RA is the armature resistance, XS is the synchronous reactance. That is the model for the synchronous generator. Okay, then so the first step deals with the initial setup. So we'll initial setup, what is this? Identify the synchronous machine in your station. Have a close look at the front panel details. Answer the following questions listed in the template. So we'll just go to the field and see, and the template, what are the things we need to know. So this is the synchronous motor generator. So this machine can be used as a motor or generator, but we will be using as a generator. So when you use any electrical machine as a generator, what you give mechanical energy to this one, and then that mechanical energy gets converted into electrical energy there. So basically, so we'll be rotating this a shaft with some external device, a prime mover kind of thing, and from there, as it's rotating, and there is a winding there, armature winding, and also there's a field winding that provides the flux. So if a flux is there and the armature is there, if the conductor is there, if it is rotated in the magnetic field, the resulting thing is the voltage will be available at the windings there. That is the basic idea of the synchronous generator. But quickly, these are the three armature windings here. So this is a three-phase machine, that's why we have three windings there. And then this is the field winding. So this field winding, it's going through this switch here. So this switch will enable the flux to be present or not be present. If you turn on the flux, the field current will be there, and then flux will be produced, and if it is turned off, the flux will vanish and the winding. So there are 4 poles there in the winding. They are connected in such a way that it produces north pole, south pole, north pole, south pole, like this throughout the circumference of the machine. And then in addition to these two, the winding and switch, there is a exciter in here. So this exciter, so it has a minimum position and maximum position. So minimum position means minimum current position. This is maximum position is maximum current position, because this exciter is used to control the current. That is the reason these are the minimum and maximum positions. Basically this is a variable resistor with a knob, like there is a fixed resistance there, and there will be a knob. It is moving, this point is moving from 0 to maximum kind of thing. So the total resistance is 150 ohms kind of thing. So that is the end of the terminal there. And what else we need to know? And here we have motor rating. Since we are not using it as a motor, so just will be disregard, will be not using this ratings there. So we will be using this as a generator. That's why we would be focusing on the on these ratings. Basically, the any machine, as you know, we need to know the power rating, voltage rating, and current rating. And since it's an electromechanical device, we need to know the speed also. That's the reason it's mentioned 120 VA. So just like a transformer, the power rating is in VA. This is also the power rating is in VA, because the power factor, it depends upon the load, not on the machine. And then it rotates at rated value of speed is 1800 RPM, and then the rated voltage is 208 volts, 208 volts. So basically this voltage, since it's a three-phase machine, so this voltage is a line voltage. You studied three-phase circuits where there is a line voltage and phase voltage. So basically, if nothing is mentioned in the nameplate, so that is implied to line voltage there. And the current is 0.33 amperes. So that is the rated value of the current. When you use it as a generator, it is 0.33 amperes. And also on the top of the winding, the ratings are given. One is 120 volts given there, and then the current rating of the winding is 1 ampere. So theoretically, this number 1 ampere and this rating 0.33, they should be same, but because of the practical considerations, it's different. So what happens when you use this machine as a motor, it would be taking 0.8 amperes. So as a generator, it can give 0.33 amperes, but as a motor, it will take 0.3 amperes, 0.8 amperes from the supply. So when you have to design, so you have to consider the highest current rating, and then instead of exactly putting 0.8 amperes as a rating, so you would be incorporating some safety factor also. So that is the reason this 1 ampere is there. That means it has a safety factor kind of thing. Okay, so that is the idea of this one. And what else? Let's see the template and see what are the questions you need to answer. So these are the questions in the data template. So answer the following questions mentioned. So you need to figure out whether it is a three-phase machine or a single-phase machine. So you need to look at the number of windings of the stator and figure out that one that I explained. And then how many stator windings are there. So basically you can see how many wire terminals you saw there. It's number 7 and number 8 you saw there, there. So there is that based on that one uh, you answer that question. And then how many rotor field windings are, oh sorry, this is the stator. So in the starter, how many windings are there? You will just see those windings and answer that question. In the rotor side, that is the field side. So how many windings are there? You just, I think 7 and 8 will give you the idea. And for starter winding, 1, 2, 3, 4, 5, 6 terminals. Those things they will give you an idea. So each winding will be having 2 terminals. So there are 6 terminals. You should be able to figure out how many windings are there. And you see exciter knob. I explained you what is the purpose of it. So that's what you have to answer it. And you might have observed that the field winding is placed on the rotor. So how is it possible to apply voltage to a moving part? That's true. So you need to figure out why, how, what is the mechanism to have in order to apply the voltage to a rotating machine. So that you need to think. So, and then there is a prime mover will be using. So the purpose of the prime mover, what is this, you should be, what is the purpose of the prime mover, you should be able to tell, because I told you at the when I mentioned about the function of a generator, it converts from some energy to another electrical energy. So that what is that prime mover is giving, you need to figure out that one. Okay, so next step is okay, measure the resistance of each winding and record in the template. So let me show it to you how to measure the resistance. Oh, by the way, there is a note here. All the 3 phases of the armature should read more or less same, because it's a if we have 3 phases, definitely all for a balanced thing, we should be having all the resistance should be same. And the field should read high resistance in terms of hundreds of ohms, but that would be in terms the resistance would be in terms of 20 or below or kind of thing. So report to the lab instructor if there is an issue found when you are doing the lab by yourself. That is the case, but let us see. Let me show you how to measure the resistance. So to measure the resistance, we need to have a multimeter which measures the resistance. So these are the windings we will be using, and these are the armature winding. This is the field winding there, and we'll be using this DMM. So I'll just turn on this, and I don't know whether you're able to see it's blinking here. So I'll set it already I set it in the kilo ohms function there. I'll be using these 2 terminals to measure the resistance, and it is in 200 ohms range. That's what we are expecting. So what we do, just we need to take some 2 color wires. Let us take black and red, because the terminals here black and red is there. So just I'll connect here to the common terminal, and this is the ohms resistance measurement terminal. So if I want to see the resistance between these 2 ends, so just connect here 1 and connect here 1, and you can see that it's showing 12.14 volts. 12.14 volts. and then if I want to see the other winding, it is showing 12.14, same thing it's showing 13, it's very close, and this is showing a 12.19, it's very little bit high, that is, but otherwise the 112 is main units, that's more or less they are same kind of thing. So I will just record that one later, but let me check this one, the field rheostat, the field winding. So the field winding at the minimum position, it is it's blinking, that means the resistance is high. So just I will go to the next range. Oh, that is also oh, maybe this is because of this switch is off, that is the reason it may be showing. Let me turn on the switch. Okay, so it is showing 950 ohm something, it is decreasing, but will not wait for too long, it's keep on decreasing, maybe because of the contact between the slip rings and the brush, and here, either here or there in the armature wind, in this field winding, it may be creating. That's why it seems to be stable now, 0.924, so 924, still it is decreasing, that's crazy. That's fine. So we want to know if it's functional or not, so we don't want to know the exact value. So this one, the maximum position, it's showing 0.314, it's 200, so it is, so this is 150, it's maximum current means minimum resistance, that means the winding resistance is showing, still showing a very 190, it's in the range of 190, something like that. So that is where how we will measure the resistances. So I will just record those values and come back to you. So these are the values I recorded. I think it's 12.14, 12.14, 12.17, and then this one 986 and 189 I got. So the next one is coupling the timing belt. So open the front cover of the prime mover and pick up the timing belt, and then couple the synchronous generator and prime mover. So I will show you in a moment how to do that one. So just I will open this one, prime mover front cover, and you can see that the timing belt is here, and that is the timing belt. And I will also open the synchronous generator module, and then I will be kind of coupling this one. You know, oh, there is a lot of gap is there. Let me first fix this one. It's not, let me align, yeah. So then now it's better. So that's what, when you are trying to work, you need to see a lot of things, whether they are aligned properly or not, whether there is some issues there. So when we see things, it will be you can easily sign and then see, and then you can rectify immediately, kind of thing. So when I'm doing, so I also check the ability of the rotation of this one. Sometimes if they get jammed, it will create a lot of heat, so that would be problems. And also I would check the free rotation of these things, kind of thing. So I'll first put this one here, and you know from the last lab, I guess, so you just lift from the with the fingers, At the same time we'll just pull down, so at some point it will go down a little bit. It's a little bit hard, so that's good. So it went in. So once it went in, so just rotate it to see whether it's aligned properly or not. So it's working fine. So we'll just now close, just pull the tabs and then push it. So that would be latching. And sometimes some they don't go, so even at least if one goes, that should be fine. So after putting, I use it. I use my fingers to pull it to see if they are any loose connection, something like that. So make sure they're tight, kind of thing. So let me go back to the manual and see what is it says. So to avoid back and forth movement of the camera, so I will try to fix it, but I recommend you to download the lab manual. When I'm reading here, you can follow it what I'm doing. You may not be able to see these things. So the next step is on the power supply. Make sure the power switch is in off position, and then voltage control knob is at 0. So that is the safety thing. So what it says is we have to make sure that is at 0 position and here, and that also should be at 0 off position, kind of thing. And then on the prime mover, set the mode switch to prime mover position. So this one you can use it as a prime mover or dynamometer. So the mode switch is here, so that has to be set it to prime mover because we are using this as a prime mover there. And the display switch to speed position here. So I think we are not bothered about the torque, how much it is giving to this guy, but we are just concerned about the speed. So we'll see only the speed, so that's why the speed position will select here. So on the synchronous generator module, here, so this set the exciter switch S1 to off position. So this switch I just initially I turned on this one to measure the resistance of this one. So I'll just keep it in off position so that at the initial there's no flux there, kind of thing. That is the reason this position is given. And then we'll set the knob at 12 o'clock position. So 12 o'clock position is the upright. So we'll just set this position. So that means when we turn on next time this switch here, so we are trying to give some enough flux to my machine so that it will produce magnetic, so that it will produce the voltage, I guess. That is the idea of that one. And then control power to DI. So make sure the gray cable which is coming from DAI is connected to the power supply. So this gray cable that is coming from DI is connected to the power supply here. So basically what we did, since it is a permanent connection, at one end we permanently connected there, and the second one we did not connect permanently, because otherwise if you want to remove two modules it will be difficult to do things. That's why one end we just keep it flexible, kind of thing. So this is connected there, and then turn on the red switch located on the power supply. So this is the power supply, this is the red switch. We'll turn on this one, and the LED and DI should be on. So this is the switch it turned. I don't know whether you noticed or not. So let me turn on and just show you. So this is off position. If you can observe that switch, this one is on right now. So that means to make sure we are giving power to the DI to function, and it would communicate there with the computer. So locate control cable box. So there is a control cable box here, a small box somewhere in your station. That is the one we located. and then pick up 24 volts power supply, gray color cable from that box. So let me see, if I open it, I can see some cables here. So this is the gray color cable it's talking about, and this is the, and what is this now? Connect that cable between DI and prime mover. So this prime mover, it needs its own power supply to operate. So it's a control power supply, it needs 24 volts. So this is the input. So you just connect here, and that one is coming from this one. You can connect either here or here, since there is no jack. So since it is coming here, so this power is available, so I will be using this one. So even though there are two ports here, just one port is enough to power it off. So the moment I turned on connected this one, you can see the LED is on. That means this module is functional now. And this one will show the speed in revolutions per minute. So RPM we call revolutions per minute. Okay, so now we'll start the software. So on the LV DAM EMS in old DIs, this is the name you will search. In new DI we will have LV DAC. So we'll forget about this one, we are not dealing with this one. So this instruction is for the new DI users, so we'll also ignore that one. So on the metering window, do the following. So first we'll open the LV DAM. So it's, if I enter LV, so the software will show up, application will show up. So if I double click it, it will open it's opening this one. Yeah, you can see, I don't know whether you could hear the click sound or not, but otherwise it's a click sound ensures that the software is communicating with the DAI. So here on the top toolbar, we have a metering window. So this metering window, if we open it, we can see, and also just let me read the instructions first. Click on the continuous refresh button to see if the program is running or not. So I usually click this one to see whether these values are varying or not. Sometimes if it is not correctly working, you would see 120 volts without applying any volt. That means it's faulty thing, kind of thing. So that's why this checking. And then for meter I3, select DC type by clicking on AC. So for meter I3, I think we are using this meter I3 for the field. So here in the synchronous machine, we will deal with both AC and DC. So DC is the flux side. To produce flux, we will be using the DC power supply. To produce the electricity, the generated voltage is AC in nature. That's why. So we deal with AC here, and we will deal with DC there. That's why this should be in I3 should be in DC mode. So that's what set. And then what is the next step? The next step is activate meter N. So we need to see the speed. So this meter N, we have to activate it. Right now it is showing some stray value, just ignore that one. Then we are running to show the correct value. And then to program meter A, so A we generally for an old meter, M5 for a new meter, so just ignore that M5. So for meter A, what we need to see? We need to see the frequency. So we can program one of the meters to see the frequency of the supply. So that's why this one is there. So this frequency set and function of E1, that means it will see the voltage waveform of E1 and it will find the frequency of that waveform for us. So right now again it is showing some stray value, don't worry about that one. And then what is the next step? On the oscilloscope, so we want to see E1, E2, E3, I guess. So we'll set for channels 1, 2, 3 for E1, E2, E3. So let us open this. So that is the no, that not that oscilloscope. This is the oscilloscope. So the oscilloscope will make sure that is running, and then channel 1 is E1, and then it is, let us see, we expand it. So that is E2, channel 2 E2, and channel 3 is E3. I think the voltage per division, how much? 100 volts per division? 100 volts per division. So we can either set like this, or you can set like this also, whichever is convenient for you. So 100 volts per division, and time scale is time base, if we had set 1.66. So 1.66 will set time base is here. 1.66 corresponds to 60 hertz. In one cycle it will display properly. That is the reason that 1.66 odd number is there. And then press continuous refresh button. I already pressed it before, so okay, these are the you can see. I don't know whether you are able to see it or not. They are changing in values. So right now no waveform, no meters count, that's why you don't see anything, but otherwise you would see some waveforms there. And then the phasor analyzer we need to set again, and data template. Okay, this video may be becoming a little longer. Let us see, quickly do these things. Phasor analyzer, E1, E2, E3, okay, 100 volts per division or 50 volts per division, doesn't matter. E1 is reference value, and then continuous refresh. And then what else? We need the data table here. Data table to measure E1, I1, E3, and okay, so E1, C2,